Hi, I'm Claire Saravia, and welcome to NASA's Kennedy Space Center. We're here today to talk about our upcoming planet hunter, the Transiting Exoplanet Survey Satellite. Join the conversation on social media and ask questions using the hashtag AskNASA. Joining us here today is Paul Hertz, the Astrophysics Division Director at NASA headquarters, George Ricker, the TESS Principal Investigator at MIT, Patty Boyd, the TESS Guest Investigator Program Lead at NASA's Goddard Space Flight Center, Stephen Reinhardt, the TESS Project Scientist at NASA's Goddard Space Flight Center, and Diana Dragomir, the NASA Hubble Postdoctoral Fellow at MIT. Let's start with our first question, which is for Paul. Paul, can you tell us what NASA is doing in the search for exoplanets?
Sure. So humans have wondered forever whether we're alone in the universe, and until 25 years ago, the only planets we knew about were the 8 in our own solar system. But since then, we've found thousands of planets orbiting other stars, and we think that all the stars in our own galaxy must have their own family of planets. Now we'll be launching TESS, and if you could run the video of TESS. So TESS will be looking for exoplanets around the nearest and brightest stars. And these are the exoplanets that will be the easiest to follow up so that we can study the planets in great detail and learn more about their characteristics.
George, how will TESS find planets?
Well, TESS is equipped with 4 very sensitive cameras that will enable it to monitor nearly the entire sky as it looks for planets. The types of planets that TESS will detect are revealed by a process called a transit. And if I could have the first graphic, it will actually show you how that works. This is the way that TESS actually looks at the sky with its 4 cameras. There are 4 fields of view that are basically stacked one next to the other to provide a swath of sky that's 96 degrees high in depth and high in height and 24 degrees wide. So altogether, TESS is able to observe about 2,300 square degrees simultaneously. So that's about 20 times what the Kepler mission was able to detect. And as a result, it will see many, many stars during the time that it makes its observations and be able to detect transits from those stars. The next animation defines what we mean when we talk about a transit. Namely, when a planet is orbiting around its host star, depending on the angle of inclination that orbit has relative to our line of sight, occasionally, a few percent of the time, that it will line up so that we can actually see the shadow, effectively, of the planet as it passes in front of its host star. And depending on the size of the planet, the depth of that transit will be an indication. And the other piece of information that we need that can only be obtained from follow-up is the mass of the planet. So if we know the mass and we know the diameter of the planet or the volume if the planet is spherical, then we can determine the density. So those pieces of information, one of which is derived from TESS, one of which is found out by follow-up observations that are done from the ground, will suffice for this. Now, TESS is going to dramatically increase the number of planets that we have to study. It's going to more than double the number that have been seen and detected by Kepler. And moreover, the planets that we're going to find will span a much greater range of host star types than was the case for Kepler. And part of the reason for that is that the passband that TESS is actually going to explore is one that extends redward from what our eyes can see all the way out to about 1 micron in the near infrared. And it turns out that stars like the Sun are actually, which emit most of their light in the range that we can see with our eyes, are actually fairly uncommon in the Milky Way. They represent less than 10% of the population, whereas the stars that TESS will actually be able to detect are actually the vast majority, 75 or 80%. So that's one of the key factors that will make TESS able to accomplish the science that we've specified for it to do.
So, Paul, what makes a planet habitable?
Well, scientists have been discussing that for a while, and there's no unanimous opinion, but there's two properties that most scientists agree are required for habitability. The first is that the planet needs to be rocky. So if we can see the first graphic, these are examples of some rocky planets that were discovered with the Kepler Space Telescope. And we think that planets up to about 1.5 times the size of the Earth are likely to be rocky based on the results from Kepler. Planets which are larger than that are probably gaseous planets. And the other property that a planet needs to have to be habitable is to be the right temperature for liquid water. If you can show the graphic now of the habitable zone, planets which are very close to their sun are too hot for liquid water to exist on their surfaces. Planets which are further away are too cold, but in this green region, the inferred temperature on the surface of the planet would be somewhere in the range where liquid water could exist. So we call that the habitable zone. So most likely, the planets that we're going to be most interested in looking for habitability are those which are rocky and those which are at the right temperature.
Okay, so Diana, how can scientists follow up on TESS planets?
Claire, that's a great question. So you can think of TESS as a finder scope because the first step in discovering an exoplanet is to first find transits. But then you have to confirm that those transits actually come from planets and not, for example, stars eclipsing each other or stellar variability or even just noise. So to do that, we're going to use a variety of ground-based telescopes of all sizes that can help confirm which of the transits correspond to real planets and which don't. We're also going to use telescopes all over the world, for example, like those in the Las Cumbres Observatory. So can I have the graphic for Las Cumbres, please? So these are the various kinds of telescopes and then the map. So we have telescopes all over the world that are going to be confirming these planets around the clock in real time, just because there will be tens of thousands of signals and only a few thousand of those would actually correspond to true exoplanets. And I'd like to note that not only scientists will be following up these planets, but also amateur astronomers can use their own smaller telescopes to help confirm which planets are true and which are not.
So, Stephen, will TESS find habitable planets?
Well, TESS is the first step towards finding habitable planets. Can I have the first graphic, please? Can I have the first graphic, please? There we go. In the course of its 2-year mission, TESS is going to observe about 85% of the entire sky. With those observations, we're going to find a lot of exoplanets across the entire sky, thousands of them. And the follow-up observations that George and Diana have mentioned are going to be really critical for us to actually understand what those planets are like. Can I have the next graphic? When we see all of these planets, we're going to discover not just a lot of exoplanets, but we're going to discover a diversity of exoplanets. We're going to find rocky planets, we're going to find gas planets, ice balls, and who knows what else. That's one of the most exciting things, is that maybe we'll find something we don't expect. But once we've found all these, some of them are going to be planets in the habitable zone of their host stars. So with TESS, we're going to know that there are planets that might be habitable. We're not going to be able, well, we're going to be able to say that they're not habitable. At which point, it will be the job of all the follow-up observations with ground-based telescopes, with space-based telescopes, with the James Webb Telescope, and so on, to try to figure out whether those planets truly are habitable or not. So TESS is just the first step in that journey. But I want to add that we care about all of the planets we find, not just the habitable ones. Because for a lot of different reasons, all the planets matter. If you care about how planetary systems form and evolve, if you care about how our solar system formed and evolved, if you care about understanding what leads to a planet becoming habitable, you need to understand all the elements in the system. And all the elements in the system include all those giant planets and the medium-sized planets and the small planets. So you really want to understand all the pieces of the puzzle for you really to answer that big question of how planets that are habitable got here in the first place.
So, Patty, what makes TESS different from Kepler?
So it is important to draw the distinction between Kepler and TESS because they do use the same method to detect planets. So Kepler was NASA's first exoplanet hunting telescope, and it was launched from here at KSC 9 years ago. And it was launched to answer one question: how common is a planet like Earth around a star like the Sun? And in order to do that, it was designed to look at 150,000 stars in a fairly wide field of view without blinking for about 4 years. And one of the many amazing things that Kepler told us is that planets are everywhere, and there are all kinds of planets out there. So TESS takes the next step. If planets are everywhere, it's time for us to find the planets that are closest to us, orbiting bright nearby stars, because these will be the touchstone systems. So the TESS mission is designed to take advantage of the fact that planets are everywhere to do an all-sky survey. So if I could look at the animation, you're going to see the Kepler field of view come up. It's up there in the Cygnus constellation, and it's in yellow. It's a fairly wide field of view, but there's one of the TESS cameras on top of it. So even one TESS camera, quite a bit bigger than the Kepler field of view. And of course, when you stack the 4 cameras together, you get a sense of how much bigger that field of view is. And we're going to be taking that field of view and throwing it across the entire sky in 2 years. We'll have 85% of the sky covered. You do see the other Kepler fields of view along the ecliptic plane. Kepler is still actually operating. It's doing an ecliptic plane survey, so those yellow squares are where Kepler has pointed. And then you can see together we'll have covered a tremendous amount of the sky when the 2-year TESS survey is done. And again, as George said, TESS is optimized to look for transits around red stars, which we know are plentiful and cool and small. And since they are small, their habitable zones are also quite a bit closer to the star. So even though we've got 27 days in our shortest period, and we've got about a year's worth of data at the poles, we will find some planets that are in the habitable zones of their stars with TESS.
Diana, how do space and ground-based telescopes work together to further our understanding of exoplanets?
Right. So as I said earlier, when TESS discovers a new planet candidate, we have to do a lot of follow-up observations to confirm whether that transit really comes from a planet or something else. So as soon as one candidate is found and it's released to the public, ground-based telescopes will jump on it, on hundreds of them probably at once, and observe them, confirm that it's a planet. Those that are planets will then be observed with a different kind of ground-based telescopes and to have their masses measured. And then once that's done, we can take the size from the transit information, as George described earlier, and the mass from these ground-based telescopes, and we can measure the density of these planets. And what that does, can I have the first graphic, please? What that does is tell us a little bit about whether the planet is rocky, like the Earth, or a little more puffy, like a mini gas giant, like a mini Neptune, for example. Once we have that information, and also information about the star that we gather while doing this follow-up from the ground, we can then go to space telescopes with a few select interesting targets and get observations with the Hubble Space Telescope, Spitzer, James Webb Space Telescope, of the atmospheres of those few planets that we have selected based on all the ground-based information. And I do want to add that even though I am very interested in planets in the habitable zone, I'm also interested in other kinds of planets. And a lot of astronomers are really interested in, for example, just hot planets of every kind, because we don't have those in the solar system. Other astronomers are interested in very cold planets, and yet other astronomers may just be interested in rocky planets regardless of their temperature. So when we say an interesting planet, we don't necessarily always mean a habitable zone planet. We really need to get the full picture to understand the planet formation as a whole.
So, Stephen, how does one use TESS to get data, and how is that data made available to the public?
Well, to me, one of the most exciting things about TESS is that there is no exclusive use period. We try to get the data out to the public and to the astronomical community as quickly as we possibly can. That has a lot of advantages. Can I have the first graphic? I think the simplest thing to do when talking about data is to actually follow the data around. That starts with the orbit. Of course, this orbit has a lot of great things about it, which I'm sure you've heard about in another briefing. One of them is, of course, that, and the reason we like it so much, or the primary reason we like it so much, is it allows us to stare at one particular patch of sky for a long, extended period of time without interruption. But one of the other advantages is that when we pass close to the Earth, we have a great opportunity to send down a lot of data very quickly. So once per orbit, we can get all that data down from the spacecraft. Now, once all the data is down on the ground, it's going to go to NASA Ames Research Center out in California, where they will use their science data pipeline to actually calibrate and reduce that data from the spacecraft. Now, this is a pipeline that's built heavily on the heritage of the same basic software that they built and developed for the Kepler mission. And that will be the first step in processing of data. When they're done with it, it will go out to MIT, where scientists at MIT will analyze the data further, validate it, make sure it all looks good, and when they give us the thumbs up, they'll send it on to the Mikulski Archive for Space Telescopes at the Space Telescope Science Institute in Baltimore, where it will be made available to everybody, and everybody will be able to get access to that data through the mast. This will be great. The exoplanet community is very enthusiastic. It's a vibrant community, and there are a lot of people very eager to get their hands on the data and start doing some great science with it. And I think that over the coming years, we're going to see an enormous number of brilliant scientific results coming out of TESS data from across the entire community. I'm really excited for that.
Patty, what is the scientific community looking forward to with TESS?
So it really isn't just the exoplanet community that can't wait to launch TESS and get the data back. It's the entire scientific community. And the reason for that is that TESS is designed to find these tiny dips in starlight, but most stars don't show transiting planets. However, we have that powerful data for virtually every object in the sky that TESS is going to see, and that's hundreds of thousands of objects per each individual sector. So there are a tremendous amount of objects in the sky whose variability tell us really interesting things about the physics that's going on there. And we have a guest investigator program that invites the worldwide scientific community to participate in TESS science and to do science that the science team is not doing for TESS. And we had a call for proposals. It was very, very popular. We got a lot of great ideas, and we announced our Cycle 1 programs a few months ago. And so those scientists and their teams are getting ready to hit the ground running and get some really exciting additional science out of TESS. And an animation here shows you some of those cool things. So stars vary. We know that our sun varies, but it's a quiet star. Many stars are quite a bit more active, and most of our guest investigator programs are going to be looking at stellar variability from how the stars are changing with time. That actually impacts whether or not a planet near that star could potentially be habitable. If the planet is receiving a tremendous amount of high-energy radiation, it could impact its habitability. But you can also look down the throats of active galaxies with supermassive black holes, millions to billions of times the mass of the sun. Those jets vary, and they can tell you something about the evolution of the jets and the galaxies themselves. There are also stellar mass black holes. There's a program that will look for those by seeing what their effects are, their general relativistic effects are on the background objects to find hidden stellar mass black holes. But TESS is going to produce an amazing treasure trove of data, and we're very excited about the legacy of TESS. And if I could have the other animation, please. TESS is pointed anti-sun, and that allows us to use other telescopes at the same time to get multi-wavelength data on variable sources in the TESS fields. So this is an example of, we talked about the small stars. You just saw a super flare going off on a star called DGCVN. That was a discovery by the Swift X-ray and BAT telescope. Those stars are very, very active, and we can use TESS data combined with other wavelength data from other observatories to get a really full picture of M-star activities and see what those potential effects would be on the habitability of planets. So we're very much looking forward to seeing what the scientific community is going to do with the TESS data in the guest investigator program, and also, once again, that archival data is available to anyone, students, amateur astronomers, people who know how to use image data. They'll all be able to get the data from the archive and do their own scientific investigations on whatever suits their fancy.
Okay, so this last question goes to George. George, TESS is launching tomorrow, so what are you most looking forward to?
Well, the fact that TESS is going to dramatically increase the number of exoplanets that we know about is certainly one thing that I'm looking forward to. It's going to be finding planets around the nearest and brightest stars. In fact, many of these stars you can actually see with the naked eye. If I could see the next graphic, that would be helpful. This is a real image that was made in January on a very cold night from a rooftop at MIT using an engineering model of one of the TESS cameras. And in this image, you can see more than 100,000 little white dots, and those are stars primarily. There may be some faint galaxies that are part of it. But the point of it is everywhere that TESS looks, you're going to see something like this. This particular patch of sky is in the constellation of Auriga, and tomorrow night after TESS launches, if you go out at dusk, maybe 7:30 or 8 o'clock, you'll be able to see these very same stars with your naked eye. And the stars that are in that little triangle in the upper center are second magnitude stars. They're among the brightest 200 stars in the sky. And one of them, it turns out, actually is what astronomers call an M0 star. It is red. It looks a lot brighter in the TESS images because of the fact that our passband extends from 0.6 of a micron out to 1 micron, and it's also, as Patty was describing, and Diana and the other folks on the panel, it's the kind of prototypical star with transits that we will be able to explore for very small planets because of the relative size of the star compared to the size of the planet itself. So we're going to be basically seeing these types of objects throughout the entire TESS survey. Altogether, the number of stars and even galaxies that we'll see will exceed 100 million such objects. The bright ones are going to be a sample of about 20 million, and those are the ones that the science team is actually going to really focus on searching for nearby exoplanets. So one of the things that I think it's good to think forward in terms of the way that the TESS data will be utilized by astronomers in the future is that it's a fairly simple calculation to estimate how many stars, how many planet systems you're going to see if you go out a relatively short distance away from our sun's location. Going 20 light years reveals about 100 such systems that we're likely to see. And as Paul said, essentially all of those are going to have planets, but the fraction, there's a smaller fraction that will have transiting systems. But we're going to know from the information that we have from those systems, the ones that are most promising to think about for potential future extrasolar probes, where we're basically going to send out a robotic system and do in situ sampling of the environment within that planetary system. There are a number of ideas have been put forward to do this with one system, Proxima Centauri b, but 50, 60, or 100 years from now, you could use those same techniques to thoroughly explore the solar neighborhood. And for TESS, this basically means that we are putting together a catalog of the very best targets for those probes. And I think it's, you know, the thing that we can imagine is there's this armada of nanosatellites that'll be sweeping out from the Earth to send back information that we probably won't be able to send people to, because it's a whole lot more complicated problem, and that's not conceivable within the technologies that we can currently envision. But small nanosats we certainly could, and so that's one thing that I think will be a lasting legacy of TESS. But the other thing is that because of the focus on the solar neighborhood and the brightest stars, we know that when this is all codified and written and correlated in the annals of astronomy, TESS will have made its mark as providing the constituent catalog that will be the reference for essentially all time.
All right, thank you, George. And now we're going to move on to our question and answer session. So we're going to start with questions here in the room, and then we'll move to questions over the phone and on social media. So if you're following us on social media, make sure to ask your questions using the hashtag AskNASA. Let's start right here.
Jay Bennett with Popular Mechanics. TESS is going to be looking at a lot of M-dwarf stars, but there's some doubt about whether or not an M-dwarf could support a habitable planet. I'm wondering if there's another type of star that there's a little bit more optimism about for a planet habitability, solar-type stars or potentially something else.
George, do you want to take that?
Yeah, the TESS will certainly look at a lot of M dwarfs because there just are a lot of M dwarfs. But it will also look at FG K stars as well, and certainly stars that are less active, if that's what you're concerned with. That's certainly a factor. But I think even saying, well, you know, there are flares occurring in M dwarfs, and therefore they're not likely to be a something that you'd find a biogenic system for. There are questions related to whether they can retain atmospheres for periods of billions of years or not. But I think the important thing for all these issues is the habitable zone does have a certain significance because we think of water as being essential for life. But I think if we've learned anything from opening up new windows in astronomy is our imagination is less comprehensive in terms of covering all the possibilities in nature. Never underestimate how ingenious nature actually is.
Let's go right there.
Yeah, hi, Mike Wall, space.com. Dan, I was just wondering, could you compare the sort of sensitivity of what TESS is going to be able to spot to actually what Kepler was sort of capable of? I mean, how many parts per sort of million darkening, like, will TESS be able to see compared to Kepler?
Patty?
Well, that's probably best answered by George, since he designed the cameras for this question.
The formal requirement specification for looking at planets in the bright range, and that means planets that are brighter than magnitude 7, which is the very limit of what we can see with our naked eye, is about 60 parts per million. Certainly, if you're looking at M dwarfs, that provides an ample signal to noise for transits that are from Earth-sized planets. When we do what's called an error budget, and we've come up with that 60 parts per million, we can't think of we really can't make that number as large as it is from the things that we know about. If the satellite works the way that it does, if the instruments work the way that it does, it could very well be quite a bit smaller than that, which would mean that it would be in the same range as Kepler. There are other aspects of the mission that I think are very promising for getting sensitive operation. For example, the readout noise associated with the TESS detectors is in the range of 6 to 8 electrons RMS. In the case of Kepler, that number was around 100 or so. So there's a margin of sensitivity from that particular contribution. The other thing that our expectation is that the stability of the optical system thermally is going to be quite a bit better than what we expect. And then a question that a major contributor to that error budget will certainly be spacecraft jitter, and that's something that our colleagues at Orbital have worked very hard to minimize. And if that works out the way that it is, we're going to beat that number by a fair amount. Another contributor when you go to deeper and deeper magnitudes is the contribution of background light. The unresolved stellar light and zodiacal light are going to be contributors to that, and that's going to be something that will vary a little bit from place to place in the sky, and we will just have to make measurements during the commissioning phase to find out whether there are any instrumental effects that cause the light levels to be higher than we think, or whether the variations will actually identify certain sweet spots in the sky that we can look more favorably. And you know, this is a question that I often ask Paul. I said, Paul, we're really interested in doing an extended mission for TESS, and in an extended mission, we're probably going to be able to improve the performance of the satellite in ways that we just can't say right now. The satellite and the instruments have been built in an exquisitely simple way, and I think the chances that it will operate much better than we expected are high.
Do we have any questions on social media?
We do. So when will the first data dump be after launch, and how often will that happen?
Stephen?
So the first data dump should be happening about 6 months after the commissioning phase is over. So it'll be right around Christmas. That's to give plenty of time for the instrument team to make sure that we understand the data, that it all makes sense, and that everything is well calibrated and characterized before we put it out there. We want to make sure that the data is of a high quality so we get high quality science.
Was the question about when the data would be archived or when the first data would come down to the ground?
When it first come down to the ground.
Oh, first come down to the ground. Well, the first data will come down to the ground during the commissioning phase, but the first science data will be coming down in June after the first orbit during phase E, during science operations.
Let's take one from the side of the room, in the front.
Chris Gebhardt with NASA Spaceflight. TESS is obviously a very small spacecraft, but a very powerful one. So can you talk about how the proposal for TESS first came about and how it evolved as NASA eventually selected it to fly? And also, in terms of the cameras and their capabilities, since we're looking so much closer to Earth than Kepler did, are the cameras able to detect dips, like secondary dips in light that could indicate the presence of exomoons or rings around planets?
I can take a stab at that. The initial idea, the germ of the idea that we had for the TESS mission goes back to around 2005 when our group at MIT was operating a very small satellite called HEDI 2 that we had built the star cameras for. They were a little smaller than what TESS had, but we actually we sort of overachieved because typically a star camera does not have very good photometric precision, but we didn't know how to make one that was coarse, so we just did the best that we could, and it turned out that the sensitivity was about a little under 1,000 parts per million. Now, with 1,000 parts per million, you could expect to detect hot Jupiters because those dips are about 1% in depth. So that would really be that would have been 10 times stronger signal than what those cameras were able to detect. But then it turned out that from the ground-based work that was being done at the time, there was an early indication that there might be smaller planets. There were only a handful of transit systems that had actually been established, and the people doing precision radio velocity work, where you can actually detect a planet based on the gravitational tug that it has to its host star. There were some hints that there were going to be things that were maybe the size of Neptunes or even things that were even smaller. So that was the first hint that we had, that there was an enormous number of what we've come to call super-Earths. We don't have one of those in the solar system, but it turns out that they're an extremely common planet. They may in fact be the most common planet. So that meant that we wanted to push to greater sensitivities with the camera. And also, the other factor is that astronomers always like to do two different kinds of surveys. Kepler is a prototypical deep, narrow search where you don't know quite what you're going to see, so you do a really sensitive job in a relatively narrow field of view. So Kepler was able to look at 0.25% of the sky. And then that led us to think about, well, okay, there's another survey method that we know about, which is a wide, shallow search. And that coupled with and that means you basically try to look at as close to, the 100% of the rest of the sky, but not necessarily so deep. So it's a different form of sampling that you actually carry out. And knowing that the real advantage that you have with doing a wide, shallow search of the type that TESS will actually be able to do is that on average the Kepler objects are 2,000, 3,000 light years distance. The solar neighborhood that small cameras like TESS can actually productively look at, they're a tenth that distance. That means the hosts are going to be 100 times brighter. And if the hosts are 100 times brighter, if you want to do follow-up work spectroscopically, if you're trying to understand the properties of the atmosphere, detect biogenic signatures and things like free oxygen or methane or CO2, the things that we know are potentially biogenic indicators. Having those extra factor of 100 in terms of photons is really important, because it means that if you try to use these types of methods to look at the Kepler sources, the Webb telescope is 6.5 meters in diameter. You'd need a 65-meter telescope to make these types of observations, and that's something that we're eventually going to have, but not for many decades to come. So anyway, this was sort of the realization of what we really needed to do, and it drove us to a system that's relatively small. So that, coming back to your question of the history, we then started to think, well, what could we do if we did something much more ambitious than just recycle HEDI-2? We came up with some ideas that involved larger numbers of small cameras than TESS ended up having. That we had an initial idea for a system that might have 9 or 12 cameras, and the idea basically evolved between 2005 and 2008 and 2009 to one in which we said, okay, we wanted to initially to try to do this as a privately funded system. MIT was very helpful for us. We had support from Google for some of the studies that we were originally doing. And then the other thing is that we collaborated with NASA Ames to actually put forward a small Explorer mission. We were a runner-up in that competition because it was still in a very early stage. And then we partnered with Orbital and with Goddard in a resubmission of that concept in the 2011 and 2012 timeframe. And then in April of 2013, TESS was selected. But when I go back, and I think this was part of your question as well, were there major differences in the instrument, the idea of how it would carry out its survey? Certainly the idea of doing it with a multitude of cameras was always there. Initially we thought in terms of flying in a low Earth orbit, primarily an equatorial orbit, but then we started thinking about the idea that we would achieve greater stability, and then in the version of the proposal that was ultimately selected by NASA, we ended up developing this concept for the TESS orbit, the lunar resonant so-called P/2 orbit that was suggested by one of our colleagues at Orbital and a colleague and a participant from the Aerospace Corporation, and then that was developed further by the engineering group at Goddard. But then once that concept study report was submitted, the number of changes that we made in it from the time we submitted it back in 2013 and now are minuscule. The basic ideas are all still there, and so it's been a long time coming. It's been 13 years, but for the last 5 years, basically everything has stayed pretty much the same, Chris.
I want to go to a question over the phone. We have.
I had the second question about the exomoons and rings.
Yes, you did.
Yes.
And the answer to that is TESS will certainly be able to find multi-planet systems. The question of whether it can find exomoons, if they are exomoons that are comparable in size to, say, the Galilean satellites, yes, we can. The question, if they were as small as our Earth, that would depend a lot on the type of host star that it actually had. If it were a mid to late M dwarf, we probably could.
And you can believe that there will be teams that are going to be hard at work looking for that in data analysis methods that they're working on now and that are yet to be imagined. There's at least one team that claims to have discovered an exomoon with Kepler, and we're going to have about the same number of planets coming out. They're around brighter stars. Some of our data will be years long, so there's definitely people looking for those very hard to find signals in the data.
Yeah, and one other thing that Paul may nudge me when I say this again. One advantage that we have for being able for being in this very long-lived orbit, if we can manage it, is that the ephemerides that you get for exoplanets will actually grow stale after a while. You need a fairly large number of accurately measured orbital periods with the transits in order to extrapolate to future missions as we go on. That has the advantage of making sure that you secure that exoplanet for future missions to discover. But the other thing that it does is it allows you to go to look for more and more sensitively at it, and that will open the window to searching for things like exomoons.
Okay, I'd like to open it up to the phone. We have James Dean from Florida today. James, thank you for being patient. Can we have your question, please?
Thank you. And I was wondering if the mission is extended, how would that change your estimates of how many more planets you might be able to find? Would you estimate that on sort of an annual basis, or is there what's the upper limit of what's possible?
Well, two of the graduate students and who've worked on estimating what TESS can do in future missions have been able to provide answers to that question in part. It depends a little bit on the nature of the sky coverage that we choose to use. One idea that we've had is that, well, we can certainly go and look at that stripe where K2 looked at a portion from the 17 or 18 campaigns that they've had. There's definitely that's a rich hunting ground for future planets. The other thing that we can also do is to tilt the focal planes in such a way that we concentrate on one of the on some particular portion of the sky. Another thing that we can do is we can try to look at the fields prior to there being what astronomers call transits. It's a different use of the word. When they're crossing the meridian at midnight, that's the natural way that TESS is carrying out the initial survey for the first 2 years. If we actually look further to the area of the sky that's going to actually rise 3 or 4 hours later, which we may be able to do depending on the properties of the satellite, that will allow us to give much more latitude for the follow-up program. That is, there will be much more time. So all these ideas are basically being looked at, and we certainly will factor that in terms of what we do with an extended mission. In terms of a number, if I had to guess, if we get another 3-year extended mission, which is what is typically asked for, it would double or triple the number of planets that we would actually find.
We had a question here in the middle of the room. Yeah.
Oh, hi. Jonathan Amos from BBC News. What's your requirements to claim a candidate? I mean, are you looking for 2 dips in a 27-day period? And can you say something about the poles? Because they're quite interesting, aren't they? Because you've got overlap there, and you could be seeing stuff that has a much greater period than what you see elsewhere.
Yes, you certainly can, and of course that's the other reason for making that very sweet spot appropriate for JWST by spending a year there. That means that we could actually look for habitable zone planets, say that are around K-dwarfs, that would have periods of a few months rather than the 2 or 3 weeks. The habitable zone for a mid M dwarf is around 10 to 14 days. So what you said about getting 2 dips during that 27-day observation is correct. There are also, as you may have seen from some of the animations, there's overlap region, so there's probably about twice as much solid angle available in each hemisphere than just that cap that you see at the north or south poles.
Do we have questions over social media?
So we've got 2 questions for Diana from social media. What type of validation of TESS data will be possible for amateur astronomers, given that transits are almost impossible to see with standard amateur telescopes? That's the first question. The second question is, Kepler used some open crowdsourcing for identifying transits. Will TESS do the same?
So those are both great questions. So the first question, the reason that even small telescopes on the ground can help is because they will still be a little bit bigger than the TESS cameras, and the detectors will be smaller, so they'll be able to actually resolve stars better than TESS can resolve stars. The problem is when you have 2 stars, or actually more than that, blended together, and you see in that blob of light a transit signal, it's really difficult just with the TESS data to know which of the stars the transit comes from. So amateur astronomers and other ground-based telescopes can help by observing with better spatial resolution, so they can actually separate those stars, and then we can determine which one is the one that carries the transit signal for future observations. And for the second question, there are plans to initiate a citizen science program. I don't have any details on that yet. I'm not the one doing it, but I do plan to help with it. Keep an eye out on the TESS website for that. We're thinking hard about how to make that work.
Well, one thing to add to what Diana said is that there's also a European mission with a small satellite called KEOPS that's supposed to launch early next year. And it has a somewhat larger aperture than does TESS, and so it will also be able to contribute to this effort because it can achieve even greater photometric precision for narrowly targeted objects that TESS will actually find. And of course, the missions are going to work closely together to utilize the capabilities that KEOPS will have.
Let's take another question on social.
Okay, here's a question for Patty. Will TESS go back and make measurements of exoplanets that Kepler has measured to test how accurate the Kepler data is?
So in our second year of observations, when we are surveying the northern hemisphere, the entire Kepler field of view will be covered by at least two of those sectors. So it will just fall out of the data automatically. We will be able to see the stars that Kepler saw, and we will look for transiting planets around stars that Kepler found transits around. We may find something that Kepler didn't find. We may be able to take some of the marginal detections that Kepler didn't claim were planets because they didn't have as many transits that they felt comfortable getting, and find transits that do confirm those. So we're really looking forward to following up the Kepler field.
Let's go back to the room. I think you, middle row, had a question. Yeah.
Thanks. Joey Roulette with Reuters. I was wondering if we could talk a little bit more about how the James Webb Space Telescope will kind of work in conjunction with TESS, and also the internationality of TESS and how other partners plan to capitalize on its finding. I'd like to hear more about that.
Paul, can you take that?
Sure. So the first part, so James Webb, of course, is a pointed telescope, not a survey telescope, as TESS is. But the most promising exoplanets that TESS discovers can be followed up with James Webb. And so James Webb will be able to watch these planets pass in front of their stars, look at the starlight as it filters through the exoplanet's atmosphere, use the very powerful spectroscopic instruments on James Webb to tease out the chemical compositions of those exoplanet atmospheres and look for whatever's there, but people are very interested in looking for what on Earth are biosignatures such as methane, carbon dioxide, water vapor, and oxygen. The second part was about international participation. So TESS does not have any international partners on it. TESS is a 100% NASA-supported mission, but the data is going to be made publicly available, so the international astronomical community will be participating in the follow-up campaign from TESS discoveries. Was that your question?
Yeah. More specifically, maybe how the European partners would maybe, like, if there's a discovery that comes about, will they send space telescopes to like capitalize on the findings? Sort of how TESS is doing that for Kepler, you know, or like what would...
I can't speak for the future plans of the European Space Agency.
There is a very active group that does astroseismology in Europe, and they did tremendous work with the Kepler data to study how stars oscillate. You learn a lot about the interiors of the star by looking at how the star rings like a bell. And they are also geared up to do astroseismology with the TESS stars to basically follow through with the same program they did for Kepler. So that's just going to come along.
Yeah, the follow-up program for TESS, which we haven't really talked about in any detail, is an enormous group of international astronomers. There are many of the groups that will be doing precision radio velocity work are primarily in Europe. There's a wonderful new telescope spectrograph that NASA is developing called NEOD that will come online in the late 2019-2020 range, just in time to really help us identify tugging back and forth of the planet due to this radial velocity effect. And then there are other systems that exist. But one of the nice things about TESS is it's encouraging people to develop these types of systems that can be used for the future as well.
Let's go back to social media.
So this is to Stephen. Do all exoplanets orbit stars? And if not, how will we find them?
It is certainly possible that there are rogue planets out there in between the stars. How do we find them? That's an extremely challenging problem. There are people who have been doing microlensing observations, and in theory with the microlensing observation you could find a rogue planet. The way microlensing works is by looking for the small relativistic effect of light bending around a massive object like a planet. And I believe there have even been a couple of claims that people have found evidence for rogue planets. One of the problems, of course, is that you can't follow up on them because they're sort of one-time events. So finding those rogue planets is going to be really hard with any of the indirect detection methods that we use, whether it be radial velocity or transits, because those depend on the host star to give you the photons you need. In the future, perhaps really large infrared surveys could find such rogue planets, but that's going to be a really big challenge for a long time to come.
Take one more question in the room over here on the end. Yep.
Yeah, on a sort of kind of more general point, I'd just pick up the European angle here. Of course, Europe, as you've said, has got Cheops coming. It's got Plato coming. It's got Ariel, which is just approved in the last few weeks as well. We do seem to be entering a period of, well, a golden period for planet hunting and for studying planets in general. I wonder if you had a comment on that.
Yes, I mean the selection of the missions that you mentioned really is going to be very, very helpful. Even the fact that they're primarily European missions is no impediment to their utilizing TESS with the same efficacy that other astronomers will be able to do. Especially another thing that's especially relevant to Ariel, and we were very pleased when that selection was made, is that there's going to be more than enough planets to go around for all of these follow-up works, and only a very small fraction are going to be able to be observed by JWST because of the proposal pressure that JWST has to do other things besides exoplanets. And the fact that Ariel is going to be dedicated to making atmospheric observations is going to be really an important thing. And so we were really pleased. The TESS team was very pleased to hear that had taken place. Plato, of course, will be a very ambitious mission. It'll probably be operating primarily a decade or so after TESS, and they're going to provide greater sensitivity in some portions of the sky. So we look forward to the new science that they will be able to provide. There's a lot more focus in Plato on astroseismology than there is necessarily with TESS. TESS is going to do it for a lot of bright stars, but that's one science area that Plato will be very powerful in terms of its capabilities.
Okay. That's all the time that we have. So thank you so much for joining us today. And if you have additional questions, please follow us on social media and ask questions using the hashtag AskNASA. And if you want to learn more about the mission, please go to nasa.gov/TESS. Thank you.